These algorithms are of course very general, so they use very flexible arrangements of gates, but almost all of these can be reduced to a single concept, namely that of a function gate. These function gates represent ordinary functions, so you have an argument x for which you obtain a result f of x, and in the context of digital information, both the arguments as well as the results can be interpreted as integers. These functions could also represent gates, such as encountered in classical computation, for instance the AND or the OR gate. And there we mentioned that not all these gates are reversible. In terms of a function, this simply means that not every function is invertible. So this means we can get the same result from different arguments, and therefore by looking at the result we cannot reconstruct the argument. And now this is a problem for a quantum computer because quantum computers are inherently reversible. So we need a special construction to implement such functions in a reversible way. This can be done very generally, but it's best first illustrated for a simple case. And for this we consider functions where the argument and the output are just a single bit. In this case we have exactly 4 different functions, and they correspond to the 4 unary gates that we encountered before. We can specify them in terms of a table. In this table we are recording the argument here, and on the other side we record the results, and for our first example of a function this would just be 0 for both possible arguments. So this function we denote by 0, 0, and these 2 zeros here in the index are simply the results that we indeed obtain. So there are 2 more of these functions, f01, f10, and f11. And for these we simply obtain the outputs 0, 1, 1, 0, or 1, 1. When we discussed these in terms of unary gates, we said that only 2 of these are reversible, and now in terms of functions this means that only 2 of these functions are invertible. So only for these 2 cases here, by looking at the result, we can reconstruct the argument, while this is not possible for these 2 cases here. How can we make this reversible? Well, we can make it reversible by introducing some additional information into this problem. And for this we are expanding the argument by an additional bit. So this argument here will now become a 2-bit number. Then we have some additional combinations for the argument, which I'm going to list all here. So we now have 4 possible input arguments. In order to have any chance to make this reversible, we then will also need a second output bit, and we are simply going to set this equal to x. So in each case we now have 2 output bits, and one of them will simply be x. So I can just copy it here. So this will simply not change. Now one of the key ideas which are already set up in the way that I've written everything is that whenever this additional bit y here is 0, we will simply obtain the correct result. So simply these entries here. There are still some entries to fill, but we have to do this so that our final function is indeed reversible. And there is actually only one choice for all of these cases. So for instance, in this case, the state 0, 0 already appears here. So we cannot place a 0 here, we must place a 1 there. And here we must place a 1. And so I'm just going to fill this out according to this principle, so that no state, no result really appears twice. So this is the general principle. We could construct a reversible version of this function, and indeed for all the 4 different cases. And I of course wanted to explain how it works, but when one then looks at the result, this has a very simple principle, which one can identify when we now translate this into a circuit. So in terms of a circuit, this function gate would have 2 inputs that we call x and y, and 1 output, and this we already know does not change. This just copies the value of x in all the different cases. And now we just need a systematic way to describe the remaining output here. And this can indeed be achieved by just looking at our construction. So in there we insisted that whenever y is equal to 0, we simply obtain f of x here. And whenever y is 1, we need to obtain the opposite result so that our gate remains reversible. And this can be simply written as a sum of y and f of x modulo 2. So whenever y is 0, we just obtain f, and whenever y is 1, we obtain the other value, which is just what we need. So this is known as a function gate, and we generally denote it as uf. So this function gate we are going to encounter many times later on in the different algorithms. And as you can see, it is actually not that complicated. It only has this operation down here, and it achieves something very useful and flexible, namely any kind of function can be made reversible in this way. Well, here I constructed this very explicitly for a function for which the argument has just a single bit, and so has the result. But looking at what we obtained here, we can now easily write down the most general case. And for this we elevate the original argument and the additional information that we added here to integers that contain more bits, and in particular m bits for this additional information, where this number m should just match the number of bits in the result. And then the output will simply be a replication of the original argument, and the output here will simply be m bits, where all these operations are carried out bit by the so-called bitwise XOR operation. But this is simply the addition modulo 2 for bits that appear at the same position in the binary representation of these numbers. Function gates describe a very general method by which we can get around the constraint of reversibility in quantum information processing. But there are other constraints, and one of them, linearity, poses a really interesting challenge, because it prevents us to copy the quantum state of one quantum bit over to another quantum bit without essentially erasing the information that we had originally in the first quantum bit. And this can be seen as follows. We want to start out with our first quantum bit in a very general state, and our second quantum bit should be initially in an independent state, some kind of fixed state which we can simply take as 0. And then we would like to transform this into the state psi psi. But if we start out from the first quantum bit in the state 0, then we should end up in the state 0, 0. And when we start out from the state 1, we should end up in the state 1, 1. But this is actually already enough to determine what happens for a general state, because if we start out from the state alpha 0 plus beta 1, and here we still have 0, then we will just end up in the superposition of these results, which in the general case is an entangled state, and not this state here, which is a separable state. Indeed, we can write this state here out, which would simply be of the following form. Which is definitely not the same state as we have obtained here. This is the essence of the so-called no cloning theorem. So while we can arrange to copy definite states of information, such as in a classical computer, when we set out to do so for general states, we instead generate entanglement. Now, this is certainly a constraint, but it is actually also very useful, as we will see in the next chapter when we discuss quantum communication. So in summary, in this chapter we introduced the notion of a quantum bit as a way to store information in a quantum system, and quantum gates in order to manipulate this information. We introduced some very simple gates, which are indeed all what we need to carry out the most flexible computations. We also discussed how we can compose these gates, for instance to create entanglement, or just now how we can then implement general functions in a reversible way so that they can be used by a quantum computer. And this is indeed all that we need for practical applications, so we can now move on to these, and we will start with quantum communication.